James Walker, thank you so much for coming on the show. I met you at an event this year, and I was hypnotized by not just what you were talking about, but how you're talking about it. So I think that's kind of unfair to both be that smart, have an accent, and wade into future topics. It's kind of irritating if I'm being totally honest.
What a lovely introduction.
I feel like I'm the pool hack, trying to play 8-ball, and here comes the pro in and just wipes us all out, and he looks better and sounds better. And
well, I don't know. I feel very embarrassed now, David. Thank you.
No, thank you so much for coming on. I thought you were so great. Today we're going to talk about energy in general, nuclear power specifically, and I'm flattered that you agreed to come on the show. Just by way of introduction, can you tell a little bit about your background, how you ended up in the industry that we're going to talk about today, and why it's important to you?
Oh, 100%. So I started off, my background is as a nuclear physicist and nuclear engineer. I got my start as a nuclear engineer with the UK Ministry of Defence. I was an engineer working on the design of secondary systems for submarines, but I did that for a while until they sent me off to do more education in nuclear physics, nuclear engineering. I got qualified as a nuclear engineer that way. And after I finished that education, they seconded me to Rolls-Royce, but they're the company that are in charge of designing the reactor systems and manufacturing the reactors that go into submarines. And I worked there for a while as a nuclear physicist in the reactor physics department and in the thermal hydraulics department, where I was doing the design of the next generation of reactors for the next generation of nuclear submarines. And after that, I got sent back to the Ministry of Defence, where I worked on the management of reactor core manufacturing facilities, as well as being one of the chief engineers at for rebuilding the Rolls-Royce nuclear chemical plant, which is a fuel reclamation plant for spent nuclear fuel. And I did that for a number of years too. But it wasn't until I moved to North America where I got more involved in public companies and capital markets. And I was over here building manufacturing operations, processing operations. And through that network, I met JU, who was the founder of Nano, and I was the second person into the company. We actually started by analyzing the market and seeing where we could fit in best, because I said, it's a very capital intensive industry. It's very well established players. And, but if we take a look at where we could fit into the market, I believe there's always a place. And we settled on microreactors. That was an area that was much less competitive, much less developed. And we saw that with the right financing structure, we could pull out into the lead of this race to produce a commercial product. And since then, we've obviously diversified into fuel, supply chain, transportation, consultancy services, but that's how we got our start. And we sort of diversified out of necessity to ensure that we could produce that commercial product for market eventually.
When you were a kid and you're sitting around thinking about, what do I want to do in life, if you did, why were you attracted to this area?
So I think there's something very attractive about physics generally, in the sense that it kind of gives you an understanding of how the universe works. I think there must be some part of all of us that's very curious about how things operate, why things are the way they are. Like if you start from physics anyway, you get smaller and smaller, eventually get down to atomic, then subatomic, and it's almost inevitable. If you want to understand how the macro work, you've got to understand the micro. And there's something very fascinating about it. It's almost like trying to understand the mind of God. If you're trying to understand, the nature of the laws of how the universe operates. Certainly, I think just general curiosity could sort of lead you in this direction, even if you don't really like maths.
Yeah. Well, let me ask you something, Art. This is very personal. We can edit this out if you want. Are you married?
I am married, yes.
So you're pursuing the idea of the mind of God. Have you figured out how to figure out the mind of your partner? Because if you have, we need to talk offline. I can read all the Holy Scriptures and talk to a lot of philosophers about the mind of God, and whether I agree or disagree, I'm tracking. I've been married almost 38 years here in just a few weeks, and from day to day, I don't know. I think I'm tracking, but I think I'd rather go recycle some fuel cells than do this again.
I think that's one mind that's very difficult to understand. I mean, I think my own wife would very happily admit that sometimes she doesn't understand herself, and that the emotion will come first, and then the reasoning for the emotion afterwards. So based on that, it gets much harder for me to interpret what's going on.
Yeah, I'm not laying any of the situation at my wife's feet. It's just my lack of ability. I think I'm tracking. I think I got the boundaries and the parameters laid out, and she has outthought me, out emotioned me, out something me again. But let's move on to something much easier to understand, and that is nuclear physics. So you mentioned there in that, thank you, by the way, for that introduction. I probably would have been more intimidated to invite you on if I had known you were that smart and capable. What you said, microreactor. So can we just start here? I'm sure people have heard this before, but I'm curious. Once upon a time, I just hear nuclear, and I'm imagining a very large facility with a lot of acreage, with a lot of fences, all the things that have real or imagined, safe or unsafe, that have poured into my mind over the last many, many decades. Science fiction films, news headlines. Are there different sizes when you say microreactor? Are there different sizes reactors, different size applications? Can you help us to understand a little bit about that?
Oh, 100%. This is a good place to start as well, just to understand the industry. But the thing that you're thinking of there, the thing with acres and acres of land, are those big traditional nuclear power plants, the sort of the Homer Simpson power plants.
That's right.
Which are like the gigawatt of power, and they're powering cities and towns and that kind of thing. And I think the US is currently 20% nuclear, and so those are all big power stations. So what we talk about now when we talk about advanced reactors is usually small modular reactors. And a small modular reactor is really anything from about 20 megawatts to, well, I'd say the biggest one is Rolls-Royce's small modular reactor. That's 470. So that's really the range, from 20 megawatts to all the way to 470. But I think most of the big companies have sort of settled on 300 megawatts as being a good range of power for a small modular reactor that allows them to both have the ability to make a lot of modular reactors and mass manufacture them, while also being not huge enough that it's going to take a huge amount of time to deploy these things. But small modular reactors are intended to power all sorts of things. So again, it's cities and towns, but with many of them. But there's also chemical plants, data centers, AI centers, big industry. And the idea here is that you're making a reactor that's much more deployable, much more modular, can be mass manufactured and deploy, and hopefully, once you can mass manufacture these things, more inexpensive than, say, a larger reactor system. And so then on the smaller end, you've then got the microreactors, and that's really from anything below 20 megawatts of output power. And then you're targeting a very different industry. There's really not much overlap between a small modular reactor market and a microreactor market. Microreactors are targeting things like military bases, remote mining projects, disaster relief areas, oil and gas projects, remote habitation, island communities, those kind of areas where diesel generators kind of operate supreme, and they've never really had any sort of challenge, whereas small modular reactors will still have to compete with gas, coal, conventional power sources that feed into the grid. Microreactors are really just competing against diesel generators. And those are really the three areas you can think: traditional nuclear, massive, small modular reactors in the middle, and microreactors, the smallest.
Why are we having, I guess one of the very first things I get asked is, why are we having this conversation now? For the longest time, other than our Navy, a lot of people don't know that at least in the U.S., most, if not all of our Navy operate small modular reactors on their ships. Why is this conversation bubbling up? And it feels like everybody, at least in my industry, is talking about it, and a lot of adjacent industries, to your point earlier, as we talk about reshoring manufacturing, as we talking about a number of opportunities for power, this is one of the center themes that we're discussing.
Yeah, this is a huge topic in itself. But if I was to give my best estimation of why this has actually happened in this way, is I would say that theoretically nuclear should be the cheapest form of energy out there. Like it should beat out everything. And the joke in nuclear is that nuclear is cheap, but the paperwork is expensive. And what's happened really, I think, is that when the US was the first nuclear power in the world. But that also means the regulator is the oldest regulator in the world. It's had decades to build up a lot of bureaucracy and regulations. And that has historically made the deployment of reactors very timely and very costly. And so, for instance, nuclear power in the US is the most expensive nuclear power in the world. But there's no reason why it should be, a fifth of the cost in China compared to the US. It's the same uranium bought on the same international markets and enriched to the same amount. But what's happened with the US is that because the licensing and the time to get a product commercialized that takes so long, that capital cost at the upfront capital cost is so large, and that led to essentially the deployment of a commercial nuclear plant being 70% of the costs were financing, not even the power plant of the capital or the construction. And I think in small modular reactors became a sort of industry's response to this impediment. So if you could have a system that could be mass manufactured, so you just need to get one licensed and then you could deploy it. And if you could do this, you can get around sort of those high upfront capital costs and apportion it. And then the capital cost per reactor get less and less and less. And so I think it really became about because of industry's response to this sort of historic baggage. Now, it is a bit different because the NRC is undergoing a lot of change now. There's been legislation put down and advanced acts being put down from government to reform it. So there's a lot spoken about now in nuclear because the NRC, the regulator, is being reformed at the same time as industry is coming up with these novel solutions to address how to deploy nuclear more inexpensively than before. And for microreactors, it's not that we've not done these before, as you mentioned, like submarines, but even what people don't realize is there's been a couple dozen of these microreactors deployed to universities in the States already, and they've been there since 50s, 60s, 70s, and a lot of them are still operating. And it's not well known about. I think tens of thousands of students walk past these things on a daily basis, and no one even knows that these things are still there. I think MIT's microreactor that they've got is like twice the size of the one we want to put out there, but it's never been done commercially. It's been done for test purposes or training or irradiating materials and experimental work. But why not make those systems commercial and power island communities, power military bases? So there's a lot of nuance. Obviously, I've skipped out, but I think that's a good overview of how it's happened. So
it's whatever the ultimate reasons are, it's fascinating. And one of the things that you just keyed on that I've recently learned this year or the last 18 months is the idea that these, other than the traditional data centers, nuclear plants, the SMRs and the micros, can be essentially built on an assembly line. In fact, that's sort of the point, is to build them in this, in such a manner. Not only does it distribute the cost, but also, as I've talked to a lot of people that are in the digital twin space and in the incremental improvement, when you've got something that comes back from the field, a piece of knowledge or a piece of information that allows them to adjust something in the construction, speed, safety, whatever, and you can enter it into your application and almost immediately improve and I know I'm probably way over my skis, but the idea there is that I can, while something's being assembled, I can influence the assembly on this assembly line. And so it de-risks a bunch of things. It is much more efficient, and I'm able to track those changes even to make them retro. And if I've got a standard design, I can go to that standard design wherever it's deployed and amend something or append something that I need to do because we've got more information. That's a fascinating idea to be able to do these assembly lines.
Agreed. And like, I saw a bit of that when we were mass manufacturing reactors for submarines, is that the first one was usually the trickiest, and there were a lot of lessons learned. And really, you hit your stride by about the fourth reactor, but they're essentially, the feedback was coming in all the time as these things were deploying and being operated. And this is something that's going to happen very much too. It's like, I am sure that with a lot of these companies, their small modular reactors the first one will be expensive. There's no doubt about it, but they will get cheaper and cheaper. And the efficiencies of these things and how they're manufactured, the efficiencies of those things will get better over time too. And we will reach a point effectively where we are able to deploy these things very quickly from order, to manufacture them quickly. And they are a lot more simple than a big reactor too. So the smaller you make it, the more simple the reactor system goes. And so you get all sorts of additional manufacturing benefits. When you get down to the microreactor, they're at a level of simplicity where you can almost 3D print most of the reactor system. And if you can do that on an assembly line, you can produce hundreds of these things a year. When you're doing that, you do get those economies of scale, but you're getting a lot of data that feeds in to just continuously optimize that process. And we could be in a very interesting situation in the next few years to decades time where you're seeing an increasing number of these, university campuses, industrial projects, remote communities. You could see nuclear all over the place, because the good part here is that it's got a concentrated amount of power. So when these things deploy, they don't need refueling for a significant amount of time. It could really be transformative across the world, for like opening up power to a lot of communities that don't have access to grid power, which is huge numbers of people. So yeah,
it blows my mind when you say it's possible that we could 3D print these things. I've had folks on the show before that have talked about 3D printing classrooms. In fact, they were working with the government of Madagascar. They had this spectacularly efficient, it wasn't really concrete. It was a blend of material that acted as concrete, and they would set up these. It's probably been 2 or 3 years now, but this infrastructure, and they would teach the locals how to do it, and they would print these things, and they looked almost like igloos, like beehives, because they found that geometric shape could snap together with other geometric shapes in a spectacularly efficient manner. And so and then they would attach solar power to this. So they would, in these areas where they didn't have classroom, it wasn't easy, they were able to use local material, literally print these buildings, and then come back and finish them, connect them to solar. It was incredible to just see this in progress. And so now I'm trying to think of, something like this that almost seems like not robust enough to 3D print it. You know what I mean? Like, wait a minute, if I can get on board with this idea of this energy, shouldn't there be something like really sturdy here? Like it seems almost too simple.
I'm sure it can be. I mean, what I would say though is that I think that the problem nuclear has always suffered, and we're probably going to get into public perceptions about safety very quickly here, but the perception between the reality of nuclear and the public perception of it is very different. So effectively, when you're talking about a robust system, a reactor is an incredibly robust system straight away. Like they can't blow up, they can't be used, they can't be made into weapons. The fuel is not enriched to enough. And even the irony is that even if you were to fire a missile at a microreactor, as an example, it would become less radioactive, because the reactors are configured so that the fuel is critical, which means it's pushed together to excite itself. Now, if you were to actually fire a missile at it, you would blow those pieces apart. And so it would they wouldn't excite themselves, and they would actually cool down. So they're an inherently safe system. And with a microreactor system, if the passive cooling is sort of built into this, or a passive safety mechanism is built in, because if everything was to break inside one of these systems, you would not get the sort of core melt that you would get with a larger reactor. And this might be dovetailing into a bit more technical stuff, but with a conventional civil power plant, the big risk of these sort of things is that they all use water, and the problem with water is the boiling temperature isn't that high. So if you can't contain that water with pressurizers, or your pressurizers break, you get a boiling effect, and then you can't take enough heat off the uranium. So it'll overheat and it'll melt. Now, no one will die. It'll be a bit like 3 Mile Island, which is, I think, is the US's worst nuclear disaster. But in that sort of case, no one will die, but you'll have a reactor that's obsolete. It's damaged, like Fukushima. It's no one is going to get killed, but you've got a reactor that's useless now. But with these more advanced reactors, you're using coolants that have a much higher boiling temperature. So if everything was to break, for instance, in these systems, the coolant can still remove that heat, or it doesn't boil over and it doesn't overheat the reactor, so you don't get that core melt. So they're much more inherently safe systems. And it begs the question why we always went the route of water. And I think it's sort of a historic legacy thing that we've done this before, and so we'll keep doing it. But there were always other better options. We've just not done them before. And for getting something licensed, the regulator likes to see stuff that it's familiar with, that it has a lot of data on. And so the water is sort of carried over for that reason. But I think small modular reactors will fundamentally change that, because they will use better coolants that are more inherently safe than a conventional water-based power system.
So other parts of the world have been continuously developing and deploying, and I don't want to dwell on them so much, but one of the things that was suggested to me is that whatever our adoption of nuclear is, we are served best by having a design or a couple designs. To your point you were just talking about, this is the thing that the regulator likes to see. They don't want any surprises. So something coming off of this assembly line, I'm already 90% familiar with it. What I want to see is the move adds changes from the last design or whatever, and I can comprehend them and give them a thumbs up or thumbs down. Do you think that's the right way to think about it, that we'll standardize on a design or two, whether that's for the micro, for the SMR, et cetera? Or do you think it will be, there is some standardization around, for example, motor vehicles. You have to fit in a lane. You have to have headlights and taillights. Like, there's safety things and there's stuff about it that you have to provide in order to operate on, as a licensed vehicle on the road. But there's a lot of shapes and different fuel types and all these other things. What is the opportunity there? Am I understanding it correctly? Will we standardize on a thing so we can get the maximum impact and then many companies can do it? Or do you think there'll be a wide variety of the design?
You're asking a really interesting question, because I would say nobody in the nuclear industry knows the answer to that question, because there's a variety of different designs, fuel types, coolants that are being put around at the moment. And of course, at the moment, every company thinks that it knows best and it's got the best solution. I think what will almost certainly happen in time is that some designs will almost certainly demonstrate better economics than other designs. And so it'll be harder for those other designs to compete against the more optimal design thing. But I think you will likely see things like solar salts, molten salts being more heavily used in reactors rather than water. I think that certainly will be an aspect to it, because it allows for the removal of big pressurized systems. It makes the system more inherently safe, which means you can mass manufacture and deploy them with fewer personnel at the location. I think that's a reasonable estimation. I think with fuel, there's a legacy thing where very already licensed fuels, trigger fuels, uranium dioxide fuels are the preference because of that legacy. But they're not the best. They're not the highest concentration. And when you're making, say, a microreactor, power concentration, energy concentration within the fuel is going to be even more important, because you've got to concentrate as much as you can. And that might push you in the direction of uranium hydride or uranium nitride, which is more dense. And I think in those sort of areas, you will see companies converging on a solution, and it might very well be uranium hydride as an example. It's a known about fuel. It's already been licensed before. There's a lot of data on it, and it's got a higher fuel concentration. But it's certainly, I think time will tell. And there are some. It's not that none of these will work either. It's I think all of these big companies, the Kairoses, the XLNGs, the TerraPowers, the NuScales, all these designs will certainly work. Like, nuclear is an old technology now. We know how to do it. We know how to do it effectively. And what it'll be is the optimization each company makes of these technologies, and as they compete against each other, the market will dictate essentially who will survives. But at that sort of point, you cannot patent the principles of a reactor, as in what the coolant is, what the fuel type is. And so a lot of companies, once it's very obvious that this is the optimal way to go, will be able to move into that area if they really want to. But I think you're probably going to end up with a few leading companies developing these systems that'll have a commanding market share that'll be hard to compete with them against, because they'll have that. It'll be like the Westinghouses of the big nuclear world. They've got experience and they've got that pedigree. And you don't want to go creating your own pressurized water reactor if Westinghouse is already there.
Yeah. It makes complete sense. As you're talking about that, I'm imagining then, like, I don't know, please help fill in the blanks. If you were to talk about, for example, you were talking about diesel before, a lot of organizations use diesel. We know how to order it. We know how to receive it. We know how to distribute it. At least in my world of a data center, we know how to do the fuel polishing. I've got the technicians for it. I got the distribution network. I know the gens that are, like, we've been using it for a long time. If I think about replacing that, which makes a lot of sense, with this really dense power that, by the way, is very clean power, where would I get that workforce? Like, if we're gonna, from the assembly of the manufacturing, even if a lot of that is automated, to the and I want to come back and talk about transportation. You mentioned that in the beginning. That's really interesting to me. But all of these things, from soup to nuts, whether it's the design that we're talking about, all the way through production to being delivered to being deployed, to maintain them. In data center world, we design, build, operate, and maintain data centers. Whether we do it directly, we certainly operate and maintain them directly. Sometimes we use a mix of partners to help us to design them and build them. But we generally own all of our data centers and we maintain our data centers, or any critical infrastructure that's tied to that. And I have family that is in Alabama. They go in on occasion during maintenance windows to inspect or the nuclear power plant there and the fuel. How is there a cadre of people? Is this an area that we have to build up? Can they transfer from one industry to the other? I genuinely don't know, but that seems like, if we're talking about all of these opportunities, not just for this dense fuel, I love that assembly line idea. Do we have the personnel, or can we develop the personnel as quickly as we're going to need these things in the next decade to satisfy the market?
This is actually, you've hit upon, I think, a bit of a problem for the industry that it's addressing now. But what historically happened is that if you look at the nuclear industry today, you've got people who are near the end of their career and people at the start of their career, and the middle was almost gutted. And what happened there is that the people who had been in there for many decades, when nuclear industry was on the decline, they stayed. But the people who were up and coming, the younger people who wanted a more innovative industry or more opportunities, they left. And so this sort of gap got put there. And so there is I would say, almost a shortfall of personnel to try and satisfy this enormous market drive at the moment. Now, even our company, we partner with a university to train people up. So we're putting into place our own PhD programs, master's programs, so we can have a stream of people that comes into our company. And we just recruited 12 nuclear engineers that were graduates of our programs just very recently. But you're right, it's going to be an issue. And when we actually, as we mentioned diesel, it's a good example to use there, because when we spoke to customers about potentially replacing a diesel generator set with a nuclear power plant in those remote locations, the first question they get asked, they say, look, we don't want to buy it, we don't want to operate it, we just want the power. And from our point of view, that means that we would stay the operators, we would deploy the reactors there, and we would sell the power. But that means that we've got to have our own personnel to run these things. Now, if we're going to be deploying hundreds of these, we can't just have hundreds and hundreds of nuclear engineers deployed to all these remote locations. So what's very likely to happen is that you're going to be able to have sort of a central location that can monitor the transient behavior of all these reactor systems, and then you can concentrate your workforce in that area. If you do that, you can actually just have more sort of technicians and mechanics or security personnel deployed to the microreactor site. And might even be able to get your staff numbers down at that site to 2 or 3 people. And say you're deploying to a mining site, they would have their own security too. So you maybe need somebody for maintenance, somebody who's just trained to technically carry out the instructions of engineers if they were needed. But most of the day-to-day operation of these reactors can be run from remote locations. And so then you can reduce the burden on how many nuclear personnel you need. But so that's one way we're trying to address it. But as a larger macro picture of the entire industry, we're going to need to train a lot more nuclear engineers. There's no doubt about it. At COP28, they were talking about tripling the world's nuclear. I think maybe they had some understanding of what that meant, but that's very ambitious because it's not just reactors that you need to build and operate. Then it's enrichment facilities, deconversion facilities, conversion facilities, fuel fabrication, fuel transportation, all of these different aspects that fit into that whole supply chain of ensuring this is possible. You're going to need a lot of people.
Yeah. We know that in data centers, we know it, if we're not even talking power, if we're talking fiber, if you're talking, any of the components that go into making a data center or connecting the world to each other, sea cables, all of the different things. It's from the design all the way through the decommissioning and the recycling. There's a lot there. The ships necessary to lay cables across the ocean and the people to do that or to maintain that infrastructure, the optics that connected all of these things. It's a lot. And that's an industry that has been pretty robust since the mid-'80s, at least as we think of modern fiber and modern connectivity beyond POTS lines. And if I'm thinking about, by the way, I made a note here. I'm not going to hold this against you because you are a man of a certain generation. We don't like the word old anymore once you hit 50. We like traditional. My kids were trying to even tell me analog. No, don't say analog. Just say traditional. The traditional way of thinking, not the old way of thinking.
Okay, well, I now know that I'm older than your kids. So
yes. Oh, you are. Yeah. But anyway, it's so I'm imagining this from the assembly of the factories to your point, the creation of the material, the designs, the deploying it, that now it's made and I need to get on transportation and safely transport it somewhere. Then I've got to stand it up, whatever that looks like, even if it's relatively speaking pretty straightforward and pretty easy, which makes me smile to say I'm talking about easily standing up a nuclear power plant of any size. But anyway, standing this thing up, and then I need to operate it, some combination of local and remote, which makes sense because that's more and more we're looking at, especially if you're talking about efficiency. It's not just manpower. I want to get a certain scale of efficiency, et cetera. And so how do I leverage that? But there's usually it's a hybrid of both remote and local, all the way up to maintenance. And it just seems like one of the things that we regularly talk about, and I know we're going to finish this conversation about regulation and safety, is just the non controversial bits of putting things together and assembling them. It's not always as straightforward as just saying, oh, well, just don't do that one today. Do this one today. In other words, stop doing gasoline and start doing diesel. There is a lot of similarity that you can do. But when you're, to stop being we're gonna put this in a coal area. My good friend Christine King over at the Idaho National Labs, one of her big passions is how do we deploy these things in coal areas because the transmission lines are there, all these other things. But the complication is there are different skill sets, same work ethic, but different skill sets needed from being somebody that works in a coal plant and monitoring a coal plant in a nuclear plant. And so how do we make that happen? That's one of the things that she's really keen on facilitating. So I know I've used a lot of words there, but it just feels like the scope of all of that is, in addition to the paperwork, it has to be built to meet the demand that we're all thinks needs to be satisfied.
Yeah, it's an interesting challenge, and what I think basically what there's a bit of history with the US too, in the sense that the US was very reliant on its highly enriched uranium from Russia, and it was sourcing a lot of it. It was sort of taking that weapons grade material as part of a treaty, and it was downblending it to meet its domestic needs. But that also allowed for sort of an atrophy of certain parts of the infrastructure. And obviously now you can see what happened with countries like Germany, where they sort of downsized that. Well, they eliminated their nuclear industry to opt for other renewables, and then ended up completely dependent on other countries for power supply, including Russian gas, French nuclear, ironically, and Polish coal. And so when you see examples like that, the US does not want to fall into that reliance on foreign energy powering, like Middle East oil is an example. So the Department of Energy at the moment, partly probably because the relationship with Russia is disintegrating, is trying to build back a lot of the national infrastructure very quickly. And you've probably seen this year, there's been big funding opportunities, billions of dollars going back out to build back a lot of the national infrastructure so it can manufacture nuclear fuel again. But that atrophy occurred because of that ability to source that Russian material. So it's kind of a unique situation. But what's quite unique now is that the government has essentially settled on, we have to have nuclear power, we have to build this back, we don't care what it takes. And because at the same time as the military is also very worried, because if we don't build back this domestic infrastructure, the military will run out of nuclear fuel that it needs for its own programs in the 2030s. So it's the government has decided it needs nuclear, the military has decided this infrastructure needs to be built back. And then at the same time, the tech industry has realized that the power requirements they have for their data centers and AI centers, their projections are enormous. And currently they can't keep taking from the grid. The grid is not built for just doubling in size in a few years to be able to power these things. So the tech industry has settled now on nuclear as being the solution. So this is sort of government, military, and tech industry of driving this big sort of resurgent interest in nuclear. So it is going to get done. It might not be as quickly done as the tech industry wants, but it will have to happen. So it's a very interesting time in nuclear, maybe unprecedented, really.
Yeah, while I happen to work for a tech company, I'm really hearing this from everybody. Like it's not. The other day, I was talking to some folks from one of the major universities. Everybody wants, and they're not necessarily saying nuclear, but what they want is the end result of affordable, safe, always available power. We don't want to have to leave our continent or perhaps even our borders if we don't have to. And they're not, that's not in their world, they just like, look, because this is what it can do for me in my research. This is what we can do for our healthcare, which was the context of that conversation. This is how we can leverage these things. And so we don't want to slow down this growth while it's related to technology or it's related to education or some of these other areas. So we need it. And so how do we make that happen? And to your point, there are parts of the grid that just the infrastructure, I see the grid as our great partners. Like we're not adversaries. It's just a matter of how do we build out infrastructure to support the whole of the environment that we need. I just want to pivot for a second. When you see opportunity like this, you see all these other things going on. There is a growing number of people that have had to come into the conversation. And so they ask you hard questions about, how is this safe? Tell me more about, and you talk about the chemistry, for example. But what are the barriers, do you think? I think all of us are trying to get better at having, not just brush aside concerns, like really address the concerns. Explain your concern to me. Let me understand it. And then let me address it in a way that you can understand. And way more often than not, we find common ground. What are some of those barriers to entry that or just barriers from public perception that you're running into? And is it equal everywhere that you go? Or is it some areas there's a greater degree of resistance than others?
So I think public perception is a very good place to start there, because that is I have gone to conferences before where I've gone to go speaking, and it's been protested, and it's very interesting because the things that I would like to say about it is that if you were to look at just a very basic metric like deaths per gigawatt hour generated of all energy sources. Now, nuclear, if you in that context, beats out everything. It even beats out wind and solar. So it's important to realize that it's a very safe technology already. And like in the worst kind of disasters, 3 Mile Island in the US, which is the worst one in the US, no one died in that instance. And Fukushima received a lot of publicity and actually led to a decline in the industry. But that's also an incident where nobody died too. And I think the problem that nuclear has always suffered is that the disparity between the reality of nuclear and the public perception of nuclear is vast, probably the most vast of any sort of energy source. And there does need to be a sort of a general level of education that goes along with us trying to build back a lot of this infrastructure and power. But it does come up a lot. Certainly when you have nuclear conferences and everyone is very familiar or they're nuclear engineers, this never comes up once. Is that if anything, there's a lot of annoyance, I think, amongst nuclear engineers that it's held to a different standard of safety than everyone else, so that it makes it prohibitively difficult sometimes because there's an order of magnitude difference in safety requirements for nuclear than anything else. So the audience very much will dictate how the perception of safety, the style of conversation will go. But even things like waste, this comes up a tremendous amount of times too, and I think there's a lot of misconceptions about waste. And one example I like to say is that if you were to take all the reactors that have ever operated in the United States, including submarines, aircraft carriers, and that goes back to the 50s, and you would take all the waste from all those reactor systems and you would put them all in one place, it wouldn't fill a football field. Like that's it. The waste is so little compared to the enormous amount of energy that we've generated. It really produces the least amount of waste there is, and it's also a type of waste that gets less dangerous over time. Is very easy to deal with, and you can just concrete it, and you know where all of it is at any one time. And the interesting thing is that if actually in the future, if we ever wanted to turn that waste into fuel, it is effectively fuel. It could actually, the stuff that we've stored as waste now could power the United States for hundreds of years. And there's always that option that we've got at our feet for whenever we need it, and we want to execute upon that. So even the waste isn't necessarily bad. It could give us enormous amounts of benefits in the future. And so like these are the sort of things that I think it's important just to keep reiterating for people so they can get the message that one, statistically the safest form of energy, two, produces an incredibly small amount of waste that could be very useful in the future. So it's big nuclear plants are already safe. If you make it smaller to a small modular reactor, it gets even safer. If you make it a microreactor, it's even safer still. And so you're right. It does need to be part of the conversation around all of this work that we're currently doing at a national level.
When I talk to people about an intermittent power source, so solar or wind, they see it, they think they understand it. Even there's sometimes where there's a misconception on its benefit, and there's a misconception on its the risks. So just because we and I'm as guilty of this as anybody, we hear and we read something, we just take it at face value and we don't investigate it further. But they can see them, they can understand it. With nuclear, there's a narrative that's gone on for a while, and it just seems like, well, let me ask it differently. How soon do you think we will actually begin to see, not in trial runs, but actually deployed, somebody's commercially bought it, it's deployed on a university, not as a test dev, but this is now powering the University of so-and-so, or it's powering these 2 steel mills, or it's doing something like that, where it's a normal, those first coming off of the assembly line, not being put through its paces, but we've agreed on solution. It's being deployed. If I talk to the natural gas guys, they're going to tell me a number. If I talk to nuclear guys, they're going to tell me a different number. When do you think really, and it could be either of those, micro, SMR, or traditional, when do you think we're going to start seeing that?
So there are already some small modular reactor companies that have started the formal licensing process. And I know there is a mandate on the NRC at the moment to be able to approve these things within a 25-month frame. I don't know if that's been put through completely yet, but even if it wasn't, they still average a 40-month licensing process. So I believe by the end of this decade, you'll see small modular reactors powering data centers and tech centers. I say them principally because the drive for power from them is greatest, that they almost don't care about the economics. And I obviously want those reactors to be as economic as possible, but they were already putting in orders. And with the small modular reactors, the orders, provided the small modular reactor can manufacture the system and deliver it, it'll be operating. There's already the power requirement there. There's already a customer base there. And the demand for these things is pretty significant. Like, for instance, we're not a small modular reactor manufacturer, but we even get asked about, can we put an order in with you for these certain different units? And we're getting a lot of orders in at the moment for microreactors. There's a lot of inquiries from island communities, from military bases, from remote communities, from remote industry, from actually existing diesel generator manufacturers as well. So the demand is there, the market is there, but it falls on the SMR companies to just get these things licensed and manufactured. And some of these companies recently have raised a significant amount of capital that enables them to manufacture those things. So by the end of this decade, you will see small modular reactors powering cities, towns, data centers, that kind of thing. And microreactors will follow up very likely in the early 2030s. And I think we will produce the first commercial microreactor too. And you'll very likely see that going to things like military bases first, but then island communities is a big one. The diesel there is very expensive, very difficult logistically to bring in on a constant basis. That results in a lot of power outages. And remote industry suffers as well because power is inconsistent. And that is a huge market, hundreds of millions of people dotted across dozens of islands that need these things. And nuclear can be delivered in a capacity that's actually cheaper than this remote diesel. Now, that makes it a very viable market.
How do you handle, I'm double checking our time. I know we're coming up on time. But one of the things in our world, whether it's the IT stack, it's the UPS infrastructure, it's the microgrid that we would build using something like diesel or natural gas, we've always got to have a ride through. So whether it's, I'm doing a maintenance on this infrastructure, I need the standby. If we're due a micro or SMR, do you have additional capacity that's not tapped into when it goes into a maintenance window? Would you have a second facility? How do you handle, because I know they have to go through, whatever the time frame is, whether it's refueling or maintenance or whatever. How do you manage that? If it's a primary source of load, how do you manage that?
So the good thing with microreactors is because we are anticipating being able to mass manufacture a very simple device, is that you could very easily have 2 or 3 or 4, but there is inbuilt capacity within all of those systems, so you don't have to run them at full power. And then suddenly you get an extra requirement, you can ramp them up. It's very simple to do. And if you were scheduling things like downtime, one could be shut down, the others could compensate. And then with small modular reactors, you do see orders being put in for multiple. And you can see it's for exactly this reason, is that multiple is better than one. I mean, even if it's one big one, that still will have a shutdown period. And, with the advantage here is that you can periodically just administer the maintenance of these small modular reactors. Microreactors are in a better situation because they won't need very much maintenance. They won't need very much downtime, and they can essentially operate at a high baseload power all year round. Small modular reactors, they might need more refueling periodically, but even then you're looking at, I would imagine, sometime around 20-year refueling cycle, 20 to 30 years. And I think with some of the larger reactor systems like the Rolls-Royce small modular reactor, that's a 60-year operating reactor. Now, obviously, it's going to be refueled during that time. but you would probably have 2 or 3 of those deployed and then shut one down to refuel, then refuel it, and then do the next with the subsequent ones, and then run it for that full 60-year period.
So you think you'd see, and this seems to make sense to me, instead of one 60 megawatt SMR, you might have 3 20 megawatt micros that are running in like a 3 to make 2 configuration, so that at any given time, one of those legs can be getting refueled or maintenance or whatever. They're still, micro. I might start off with 2, and then I add that third, I need 20 megawatts, for example. I'll have 2 of them. Yes, I have 40, but I don't run them each at their maximum capacity. I run them at 10 each or whatever it is. As I start creeping up towards that 40 megawatt need, 20 megawatt need, well, then I would add a third. So at any given moment, we've got ride through, we've got resilience. I mean, that is traditionally, maybe not all facilities need that kind of ride through, but if you're a military base, if you're the 911 system for a sheriff's department or, FEMA or something like that, you got to always be on. You can't be off for any period of time. Do you see that even in the SMR world? Maybe instead of one 300 megawatt, I've got 3 100 megawatts, and I can, at any given moment, I'm doing 200 megawatts. I'm just thinking out loud. I probably shouldn't do that with a, nuclear scientist.
No, but you're right. It's like actually, we've seen orders from state level actors that are and it's not just that they want several at the same time. They also want to scale up over time. And actually, some big data centers, they might start off wanting only 500 megawatts. That's still a lot of power. But over time, they envisage 2 gigawatts, 4 gigawatts of power. And the nice thing about a more modular system here is that you don't need to bring that all up front. You can have 1 brought in or 2 brought in at the same time, and then ramp up, ramp down as you need, then bring in another one and bring in another one as you need. And you might see a more sort of a coalition of tech centers into one location as you scale up the power of those different locations. But certainly that's the big advantage here, is that you can scale. And typically you couldn't have done that with a traditional power system, like a big nuclear power plant. You can't just build a big second one after you've built the first one.
Yeah. I'm fascinated with the idea, not just the technology and all these other things, but what we don't talk about a lot is the time to get transmission infrastructure built. And so the need, whatever the energy source is, to get it closer to the requirement is a real thing that everybody's talking about. They're hard problems. If they're easy problems, we wouldn't be talking about them. Do you have a few minutes for a couple more questions, or should we?
I do. Yeah.
Okay, great. Here's my first one that please correct me if I'm wrong, but one of the things that I've heard, we talked a lot about economic benefit, safety benefit. I'm a big believer in energy sovereignty. I just think that's a super important thing for an island, a nation state, whoever you are, to have energy sovereignty should be important. That's with all of that said, we also have sustainability goals. Where however it is, whoever you are as an organization, whatever your motivation for approaching those things, you reminded me of this earlier when you were talking about all of this waste is here in this football field. It's, as I understand it, nuclear is spectacularly clean power. And so if you could talk about that. And then the second part of it is the waste that we do have. I've read a number of articles. I don't know how accurate they are, but the potential of recycling, you were talking about that earlier, where you could get the shelf life of these things down, reuse that fuel. Is it fully developed yet? No, but there are people that are really engaged and interested in doing that. But you know where the waste is. It's right there in that concrete block, as opposed to other waste, which is somewhere in the atmosphere. It's somewhere out here. And so for a lot of reasons, if sustainability is really important to you, in addition to these other economic things and safety things that we've talked about, nuclear should be something you should investigate closer, because it absolutely can help you hit those goals. If not, some would argue it's the only one that could really help you hit those goals. Can you talk a little bit about that?
Oh, look, for sure. So I think on the waste issue, that's something that's very interesting to touch on to explain a bit more about it. So this is something we can already do and we know how to do. The reason why we've not reprocessed this waste in the past is a proliferation thing. So the US has taken sort of a blanket approach of just prohibiting reprocessing of fuel. Now, it's very unlikely that'll perpetuate and it'll continue. And there will be amendments to allow for certain reprocessing. But the reason why it was a proliferation issue is when you have a reactor system and you are having chain reactions with the uranium, you create things called fission products. And one of those fission products might be something like plutonium, as an example. That's obviously in small amounts, but the US has taken an approach where you just concrete it and it sits there, and then there's no risk of anything happening at all. But it's actually very easy to manage that process. And actually, in the UK, I was part of a nuclear fuel reclamation program that was doing exactly that with spent fuel plates. So we know it can be done as can be done for a while. Once the US starts allowing for a safe way of recovering that fuel, there's an enormous amount. And to give you some perspective, say we were to operate one of our microreactors for 20 years or whatever it is, burn up of the fuel itself would be less than 1%. So 99% of the fuel in our microreactor is actually unused, effectively. So if we were allowed to reprocess some of that fuel, we would have almost essentially a new reactor there, because the uranium, the power in uranium is so dense that even after 20 years of outputting full power, you've used up barely any of the raw power within that uranium. So there's this huge potential there. And even in big power stations, like the big civil power plants, maybe the burn up's 3%. And so effectively it's almost new fuel. It's almost brand new fuel that we just need to take these fission products away from, and then you've got this uranium you can just reuse again. So there's one big critical aspect, but it's also on the sustainabilities. Carbon emissions are very important to a lot of people. Zero carbon emitting energy there. And in terms of, how sustainable is nuclear energy? I mean, there's enough, even in the sea, there's enough uranium, I think, to power civilization until the end of the earth, until the sun consumes us. So we'll be fine on that front too. It really could be an enormous benefit to mankind. I think that's the real truth about this. And it really is incumbent on us to utilize this enormous gift that we've got available to us.
Yeah, I couldn't agree more. What I don't understand, I'm not maybe smart enough for those who really resist this idea to have pointed questions. I don't know enough about it. I wish we would more and more, whatever the topic is, have thoughtful people who know their that have an area of expertise, and have a public discourse honorably. It could be pointed, but honorably, about all of these energy sources. It seems to me, as human beings flourish, I say this all the time on my show, the more we use, the more we want, and the more we want, the more we make. I've got a TV that hangs on my wall that's much bigger than my plasma TV from 20 years ago. It's a fraction of the weight. It's a fraction of the energy. And it's 100 times the, pixelation. We got quantum dots in these things now. It's crazy. Yeah. So we don't want to slow down innovation. Like, we're consuming it. I want to use it, but it's much lighter. It's much less energy intensive. There's so many things that these technologies will allow you to do. Robot surgery, where you can see, not at the molecular, but you can see so crisply. And so I don't want to slow down the innovation. It's not just for entertaining pet videos or whatever. It's for all of these really important things. But if we're not allowed to have a conversation, it's almost impossible to do two things. One, demystify what's not true. And two, where there is real risk, how do we hold each other accountable? Like, we need to make sure it is safe and designs are safe, and that from soup to nuts in all of these things, we don't want accidents. We don't want anything to happen. It's our children, it's our citizens, it's our neighborhoods, right? I think we're all for those things, but it feels like sometimes we protect some conversations and don't allow others. And I'm just hoping that we can facilitate the conversation, and then we, the people, decide what suits us the best for our ourselves, our families, our neighbors to flourish?
Yeah, I think you raise a lot of really good points there. I mean, even just mentioning, as you mentioned about children there, that's kind of our investment in the future. And I've got my own kids, and I really want them to inherit a world that has lots of opportunity in it. And energy is one way to ensure that, because it is the base load of all industry and enabling innovation. And provided power can be made readily available and cheap, there's more opportunity for you to innovate and create other industries. And it's the bedrock of everything, essentially. My children are my investment in the future, because I won't be here for that much longer. So, we do need to have these conversations. It does need to be done responsibly. I don't think people should shy away from conversations around safety or waste or any of these kind of things. I think these are important conversations to have. And by having these things, you will demystify this industry and these technologies, and it will make people ultimately, I believe, more receptive to them, because a lot of the misconceptions about them will be assuaged.
I agree. By the way, I love how you worked in the word assuaged into my, I think that's the first time ever in this podcast we've, I heard these two Brits talking the other day, and they said, you might have heard this, I think it was on the Chris Williams podcast, and it was these two guys, and they said, why do you think everybody reacts to our accent the way they do? And one of the things they said was, it's like you're from this island, and everybody on that island is a salmon fisherman. So nobody cares. You're all in salmon fishing. But the second you leave the island, nobody knows what a salmon is. And so you're this exotic thing, and you sound more learned. You sound, like all of these other things. And then you add to, after that, James Walker, PhD, with, your salmon fisherman accent. It's pretty. Anyway, I'm going off on a tangent.
Yeah, well, maybe it's helped me. Maybe it's made me sound smarter than I am, so it's helped me in my career. I don't know.
Yeah, no. I think nuclear scientist PhD helped there. But let me ask you this: or just an observation and then a question. My observation is, not in every case, but regularly, when I'm talking to people that are in the space of generating energy, the non-nuclear people generally poo-poo the time frame. The very few are I can't imagine really anybody or recall anybody that says this is not a future technology. But for many of them, it's far in the distance, and they're not necessarily adversarial, but they're not embracing. And that could be natural gas, that could be hydrogen, that could be solar, it could whatever. I haven't talked to enough hydro people to know what that camp is. When I talk to nuclear people, usually they're like, look, we want to see all forms of energy, whether it's in the grid, whether it's in these locally deployed, like we've been describing with micro, whatever. Like what fits where? What fits for the load? Is this base load? Is this is it up and down like a blockchain, or not blockchain, cryptocurrency or whatever? Is this something that can spin up and spin down? Even in a data center, not all infrastructure is tied to a UPS. It doesn't need to be. It's like a light. You can turn it off, you can turn it on. And so it's tied to the backup generation, but it's not tied to these other things. So you don't have to have the same level of consistency or whatever for all the things in the infrastructure. Why is that? Is that your observation as well, or am I just, because of my little narrow world, experiencing it? And how, when you interact with people like that, do you help them to see, look, it's all, we're just trying to have energy sovereignty, and we're trying to solve the problem, the things that fit today, and moving towards the things that'll fit tomorrow.
Look, it does have to be a combination of different solutions, and it's not Norway. You can't run the whole country on hydro, because you don't have a population of, what's Norway's population, 5 million or something like that? You don't have all these dams all around. It's a big country with a lot of a very diverse environment. And so when you can access geothermal, great. When you can access hydro, great. I've got a lot of affection for gas. I don't know if I'm supposed to say that in nuclear, but I think it's been enormously beneficial. It's actually been responsible for the US being, I think, having the largest drop in carbon emissions of any advanced country in the world, effectively because they switched from coal to gas. So it definitely has its place, and maybe coal even has that sort of a place in that future too. Like, it's been enormously beneficial for mankind. And, I know there was an enormous enthusiasm for wind and solar. I think baseload power for those energies was always very difficult to maintain, even with big storage facilities that were being brought in to assist them. But there still can be a major component of that solution. Big in areas where you've got large amounts of acreage at your disposal with very good sunlight or wind conditions, why not? Like, why not have that forming and generating enormous amounts of power? Nuclear is definitely going to be part of the solution because you can put it anywhere. It's not locationally dependent. It's a very high energy concentration. It's the highest baseload power. It is zero carbon emitting, so it does meet those climate requirements. And like it obviously, where there's a massive dam, you opt for hydro. Where it's in the middle of the Arizona desert and you want to put a data center, very likely nuclear is your best bet there. We can be very strategic with how we do these things, and I never want to say one particular power source is better than the other because, it's like boxers. Some styles make fights.
Right, absolutely. My wife, if she listens to this, would completely disagree with you about her relationship with gas, mostly because I'm full of it. She doesn't appreciate it, but that's a personal story. So, as we wrap this up, what's our call to action? What should we? If people are hearing this, whether they're bullish on it or they're reluctant about the idea of nuclear power or its timeliness or its safety, how do you want people to think about it, and where can they go for more information?
Well, I mean, for our own website, I mean, nanonuclearenergy.com, and we're on X and Facebook and all those, and Instagram and all those kind of things. But I think if you're your own listener and you want to be involved in the industry, you can't go wrong with an investment into one of the nuclear companies at the moment, because I think this is an inevitable industry. It's being pushed by DOE, DOD, and the tech industry. So, and it's also a way of supporting it too, to ensure that it is more likely to happen. I mean, I think it is inevitable at this point, but there could be, to the average person, there could be a real benefit of having an involvement, even if it's a small involvement, in this sort of burgeoning renaissance period of nuclear. But generally, I think there's a lot of really great information out there. I think the Department of Energy, the national labs, they have all sorts of public information that can be readily accessed that can give you a tremendous amount of understanding of what SMRs are, what the technology is, how nuclear energy works. And look, I know nuclear, where we talked about timelines just now, timelines can sort of give an industry a bad name, but I would say on the fission side of nuclear, like conventional reactor systems, SMRs, the timelines are usually quite prudent. Fusion is always 20 years out, and everyone's always estimating it's going to come. And maybe that's carried over to everyone being suspicious of timelines, because I think even now they're saying 20 years, but they were saying that 20 years ago when I started in the industry.
Right.
So now,
what haven't we talked about today that we should have? I feel like we've covered a lot.
Well, we've covered a lot. I don't know. I think nothing comes to mind, but yeah, I think we've had a really good conversation about all this.
Well, James, thanks for coming on the show. We will link to Nano and to your profile so that people can reach out to you if they have any questions. And I can't wait to have you back on maybe in the next year or so, and just how have we evolved? What's going on? Where are the wins? Where are the things that are obstacles that we still need to overcome? I look forward to our next conversation.
Me too. Thanks a lot, David.
Thank you so much for coming on. Hey, if you like that show, like the button. And if you loved it, subscribe. We'll see you next time, everybody. Have a good one.